All right, so thanks for having me. So I'm Dr. Christy Edwards. I'm the Deputy Exploration Architect at Lockheed Martin Space. My team looks at the kinds of missions that we want to do in the future, both to the moon and to Mars. And we try and figure out how to get there. What kind of systems do we need to develop? What kind of technologies do we need to advance to enable those future missions? The kinds of missions that I look at range from like 5 years into the future, all the way to like 20 years into the future. And then technologies, I'm also trying to look at what are those long-range technologies that could really change how we do things in space. A little bit about my background is I grew up around here, went to Chatfield High School up in Littleton, Colorado, and went to MIT to study aerospace engineering. Did my undergrad and then my master's after that for another 2 years, and then started working at Lockheed Martin back in 2016. And back then, I started as a guidance, navigation, and control engineer. And on the Orion spacecraft, I was really eager to work in human spaceflight and help astronauts land on the moon again. And then from there, I joined a leadership development program that had rotations within Lockheed and did rotations through spacecraft operations in deep space, working on some Mars orbiters, and a comet mission and a moon mission. And that was really exciting work because it was working in a mission control room, and you'd send commands to the spacecraft and then hear back the spacecraft how your commands went. And so it's like almost like instant gratification of you are always felt like you're making a difference that day. And then from there, I started a PhD program while working at Lockheed at Stevens Institute of Technology. And after working on that PhD for a while, I really wanted to get more into like research and development. So that's when I joined this group. So I worked for the Advanced Programs Group at Lockheed Martin for commercial civil space. And so we do those kinds of things I was telling you about a little bit ago, where we look at what are these future missions and what could they look like and how do we get there. So we're truly living in an exciting era in space exploration. It's the Artemis Era. So we have plans to establish systems and infrastructure that enable sustained lunar missions, provide the basis for a lunar economy, and develop capabilities for Mars. So for this presentation, I'm going to talk about the buildup of lunar infrastructure, at least how we envision it, and architectures that can adapt from initial phase of Artemis, where we're going back to the moon, returning to the moon, and exploring different sites on the moon to figure out which site could be the best location for a more permanent base. Also scouting out resources on the moon that we could potentially use for in situ resource utilization, or ISRU. And then, so setting up that more exploratory phase on Artemis, and then transitioning from the exploratory phase to a phase that's more, that it has a more sustained presence, where we have a more permanent lunar base and build up the infrastructure to support that kind of base and any lunar economy that can grow from that. And then I also want to talk about how this sustained presence on the moon can enable future Mars exploration. So here is a graphic for how infrastructure can build up on the moon. We have this first mission is what we envision for like when we return to the moon in the coming years. So we have for this first mission, one of the things that can be on the surface to support exploration is the unpressurized rover that's shown there. And then in each subsequent mission will occur on about a 2-year cadence. And as each mission goes to the surface, we can place more and more infrastructure and vehicles and systems that can support this, the growing plans for these Artemis missions. So the mission 2, we have that pressurized habitation starts to be used. The pressurized habitation allows for crew to explore further out from the lander site. Also, we have the VSAT, which is the vertical solar array technology. It can provide extra power to help power the rovers. Also, for ISRU investigations, there's the Viper mission and some other robotic missions that are planned in the near term. And those missions will be looking for how accessible ISRU materials are. Like, can we get to them? How abundant are they? And then from there, we can start to do demos like O2 extraction or water extraction from permanently shadowed regions or PSRs. And then as we build up, yes, in subsequent missions, we can have things like pressurized habitats. And then also NASA is planning a fission surface power demo. So it's delivering nuclear energy sources to the moon. And the fission surface power can potentially provide even more power than like a solar array. And what we found in our studies is that ISRU, the amount of material that you can produce, is limited by the amount of power you have available, and also by the amount of resources that are in the location that you're at. So fission surface power could really enable that ISRU activity. Also, we have the first ISRU pilot plant envisioned here. In the meantime, comm satellites, the number of comm satellites in lunar orbit can grow to support the communications for all these missions. So I think I'd like to go ahead and take questions as we go. So do we have any questions for this one? Yeah.
I think you can grab that circle and pull it out of the way.
Oh, that'd be good. Let's see. Thank you.
And then you're only working on a landing pad on the 4th mission, so is there concern about debris blowout damaging existing infrastructure?
Yeah, so as we're looking at that transition from doing like exploration missions to various sites around the lunar surface, but as we transition to more permanent base, we are concerned about landers shooting out debris as they land and that impacting the other things on the surface. And so one of the ways that could help mitigate that is by doing a groomed landing pad or like setting up burns and stuff like that that can try and block that debris that can get kicked up.
Quick question.
Sure.
So what role exactly do the human astronauts do there as opposed to like just sitting on a rover? Like why would we send humans there? Like, you know, what's their purpose?
Well, for these missions, the humans can do more efficient exploration than rovers. So rovers take a while to explore surfaces, while humans can do more efficient exploration. And I really see these kinds of missions as being a teaming of humans and robotics. It's the human robotic teaming where the robotics can enhance the human activity enhances the robotic activity. So through like utilizing the strengths of both of those areas, we can explore this region more efficiently. Yes. Yeah, the question was about have we done research into mitigating the lunar dust problem. And lunar dust is a big problem because of the lunar dust is very sharp, lots of shards in it. And when it gets on stuff, it sticks and it gets everywhere. And so, yeah, that's actually one of NASA's big initiatives right now. There's the LSIC group that one of their areas of research is looking into lunar dust, and we've participated in that and done some studies ourselves as well. So we have various ideas on how to try and remove it, how to try and keep it out of important parts. So yeah, it's definitely a problem, and definitely one that is going to take several approaches to try and mitigate it. So this next slide shows some ideas on how these elements of these sortie missions to the surface, where they're going to various locations, how those elements can adapt to be more part of a lunar base, something that's more permanent. And so in this case, we have the VSAT, which is the concept is to be able to pick it up and move it from site to site. That when you transition to a base, it can be placed on top of like a peak where you get a lot of sunlight, and then run a cable down to a microgrid hub. And similar with the FSP elements, whenever they start to be available, is also to be able to run, those have to be 1 to 2 kilometers away from wherever you have astronauts because of the radiation. And so you can run cables from that to your microgrid hub too. And that would be like the hub of power for various other things like the habitats, ISRU plants. And then as new technologies are developed, the architecture can adapt to incorporate those new technologies like power beaming into craters. We think that a good amount of the ISRU material, like water, could be more available inside the permanently shadowed regions, inside craters. And so one of the challenges is figuring out how do we get power into these dark, cold regions in order to power like excavators. So this was one of the studies we did earlier this year. We're looking at how could the power needs grow over time, and then also how could the power supply grow over time with some of the current plans. And so it shows that, well, in our analysis, we're looking at how rovers could start getting energy using like VSAT, the solar array technology, to like a supplemental charging to charge them up in between traverses. And then as you start to incorporate habitation, then the power needs grow significantly. And then ISRU can start up at a low level when you're just doing like your demo plans, but it really ramps up whenever you start to produce propellant for missions, to like refuel missions, or propellants to send up to a depot in orbit. And it also ramps up like for producing consumables for crew to breathe. Over on the power supply side, you have I've shown the power supply that could be provided by 2 VSAT elements and a fission surface power demo. All of those elements are all right now designed to provide about 10 kilowatts of steady power. And then I have a ramp up when a fission surface power plant arrives that could potentially provide more power. Oh, I should say that with this analysis, we showed that with 2 VSATs and a fission surface power demo, it was able to meet those early power demands for this growing infrastructure. So some of our ideas around this growing infrastructure and what it could support is that it could help provide the basis for a lunar economy. And so this lunar economy, we envision it being very water-centric. We call it the water-based economy. And in this water-based economy, what can happen, or at least how we envision it unfolding, is that the government could be an anchor customer, providing like a steady demand of like propellants for their missions to the lunar surface, and also propellants to start fueling a Mars transit vehicle. And over time, as they kind of show the technological capability of producing this kind of ISRU material and the feasibility of it, that it can grow into a vibrant water economy. with multiple providers, multiple users, people using the propellants or organizations using the propellants that are from government, commercial, international. And so we just see that this could end up catalyzing into a thriving economy. And I should say back here, one of the vehicles that, or one of the concepts that we've been developing that could really drive this kind of economy is the Mars Base Camp concept. It's a Mars transit vehicle that would be built up in lunar orbit, and then it would transport astronauts from lunar orbit to Mars. So I just realized I thought ahead with all these most recent slides without pausing for questions. So are there any questions for what I was just talking about? The last couple slides? Yes.
How many years is the lunar water resource it can last? Like 1,000 resource, 100 resource?
That's a good question, and we actually don't know. We know that the recent robotic missions, all the orbiters that have been going up in the last like 10 years or so, we've been detecting a lot more water than we ever expected on the lunar surface, at or near the lunar surface. And it's so intriguing how much is there, but we don't know how accessible it is. So these early robotic missions that are going in the next like 5 years, they'll really help us to determine if it's mineable and how much it is there, at least in the areas where we're driving those rovers. We'll help hopefully get a much better picture of that. Yes.
I'm just curious, talking about you have the 4 missions, and then over time you're talking about supplying a number of different things with fuel from this water. Is there any sort of time scale that you're hoping that you would get to where then you would, where the 4 missions would happen, and then you would have enough where you're able to supply other spacecraft?
Those first 4 missions are supposed to happen about every 2 years from each other. And then I think that from those we'd start to build up that potential ISRU, at least investigate and understand how much ISRU materials are available, and then from there starts to build that lunar economy. So talking like 10 years or so of start of building that up.
Okay.
And here is, so I wanted to also talk about our Mars Base Camp design. So the Mars transit vehicle that NASA envisions would be built up at the Gateway. So the Gateway is a location in lunar orbit. It's in the NRHO orbit, in our near rectilinear halo orbit. And the Gateway is where the Orion takes the crew of astronauts from the Earth up to that Gateway. They transfer from the Orion into the landers at the Gateway, and then go down to land to the surface. And when the mission is over, they come back to the Gateway, transfer back to the Orion, and then come back to land. And the Gateway is also going to be the hub where the Mars Transit Vehicle is built. And so this is our concept for our Mars Transit Vehicle. Back in 2017, we developed the one that's over here on the right. That one is a chemical propulsion Mars Transit Vehicle that we called Mars Base Camp. And this year, we updated, or we developed a new configuration for Mars Base Camp. And that is our nuclear thermal propulsion configuration. So this Mars Base Camp uses nuclear thermal propulsion. We have NTP engines and tanks here on the right and over here on the left. And having 2 of them provides redundancy and also capability for this long mission. We're envisioning that the mission, this particular vehicle we've sized to have enough propellant in these 6 tanks plus these 2 main tanks to supports both conjunction class missions and opposition class missions. I should probably tell you a little bit about what that means. So the conjunction class missions are longer duration missions that last about 3 years to get to Mars and back, and they spend about a year at Mars doing mission supports in Mars orbit. The other kind of Mars mission, the opposition class mission, lasts only 2 years, but you only get a month at Mars. So it's a very short stay at Mars to do the science and investigations that you want to do. But we've sized this vehicle to be able to support both of those kinds of missions. Yes.
Yeah, I don't know much about nuclear thermal propulsion, but does this include like refueling at Mars, or does it have all the fuel for the whole mission?
This one has all the fuel it needs for the total mission. And actually, you only need like 2 to 4 of these tanks for the conjunction class mission, and then 4 to 6 of these tanks for the opposition class mission. And it depends on what year you're going on how many tanks you'll need. So the orbital dynamics are very complex, but actually pretty fun to look at for this kind of mission. We have an inflatable habitat. Also, there's a habitat nestled inside the tanks where we're putting the crew quarters. So that when it's inside the propellant tanks, that provides a little bit of additional radiation shielding. And this is a docking node where the lander can dock. So, what questions?
So as far as the tanks, we envision like the propellant coming from the moon, except like for like the water economy, would we see the propellant being shipped from the moon to the lander, or would that propellant come from the Earth, or do you guys not know yet?
I think it'll probably be a tipping point. That what we'll see first is that the propellants will be launched from Earth. And then and I'm thinking overall for like the landing missions to the lunar surface and from Mars base camp, that the propellants originally will come from Earth. And then at some point, the propellants that's produced by ISRU will become more affordable than the propellants launched from Earth. And that point will be a tipping point where the lunar economy will really just take off, because it will be more affordable to get that propellant from the lunar surface. What's your question? Did you have one? Oh, okay.
Well, yeah, as I say, I think you explained it, that this is intended to enter Mars orbit. It's not like an alternate cycle where it just kind of goes.
Right.
Leaves
Yeah.
something and comes back around.
Yeah, the question was about, is this a cycler, or is this one that design that enters Mars orbit? And this concept is one that enters Mars orbit. We are interested in looking at cycler concepts too. But for this particular study for this year, we're looking at one that enters Mars orbit and stays there for 30 days or up to a year. So we did some ISRU demand scenarios. So these are some scenarios that we ran through of what kind of demand could be built up over time for these kinds of lunar landers, or a Mars. This is our Mars lander concept, or our Mars base camp concepts, both the chemical configuration and the NTP configuration. And so for these lunar landers, we predicted that they could transport about this amount of propellant from the lunar surface up to a propellant depot. And then this is the kind of demands that these kinds of missions would need of this kind of material. So once you start building a Mars mission, that demand can really climb. And here's more about that mission design, or that what the mission could look like for Mars base camp, where when you enter Mars orbit, the reason why we call it Mars base camp is because it's like setting up a base camp in Mars orbit, and from that base camp you do your expeditions out from it down to the Mars surface or out to explore Mars moons. I did a base camp with the Denver Museum of Nature and Science probably about 8 years ago, where I went on an expedition to Utah, and we were digging up dinosaur bones. And we had this base camp that we set up, where we set up our tents. It's where we had our tents, where we had all of our food, the campfire, everything like set up as kind of our base of operations. And then every day we'd go out on sortie missions out into the field to go dig up dinosaur bones. And then when we were done at the end of the day, we'd come back to base camp to eat and to sleep. And so this kind of base camp idea, that's why this one's called base camp, is that it's setting up a base camp in Mars orbit. And you can do your surface missions and Mars moon missions from that base camp. Other things that you can do from base camp is do reconnaissance and direct investigation of the Mars surface using robotics. So with a human on board at Mars, you no longer have that communication latency with Mars, where to talk to anything at Mars, including to talk to any of the robots at Mars, it can take up to 20 minutes to send a signal, and then another 20 minutes to hear back. And if you have a human there controlling the robots, you don't have that kind of delay. So they can even more joystick the robots in the exploration. And then also they can curate samples on board to retrieve the samples that are brought back up from the surface and analyze them on board, figure out what's the most important samples to bring back to Earth. And then talks about missions to the Mars moons, Phobos and Deimos. We have a concept where we can break off one of these Orions with the tank and engine, and that can do its own mission to the Mars moons, carrying a kind of excursion module, kind of like this one shown here, that can break off and attach to one of the moons to explore it. So, overall, the Mars Base Camp mission that we've developed, it's an idea of what's possible with our current technology or technology that's currently under development. And it's to show, it's not necessarily the only solution for how to go to Mars, but it's a way of saying this is something that's possible, that this is an idea that can work, that we can work towards. And as we do these missions to the lunar surface, starting with these robotic sortie missions to explore what kind of ISRU materials are available, and we expand to human sortie missions, and then expands to a more permanent sustained presence with like base site and ISRU production, a more steady ISRU production, that can fuel the kind of mission where a Mars transit mission that can build up at the gateway. Yeah.
Can I just ask, you're saying that you're developing this with the idea that it's really pretty much available technology and something that could work. And with that being said, I know there's got to be a lot of challenges. What do you think are the greatest challenges that face a system like the one?
I think, at least for the nuclear thermal propulsion, it's one of the big challenges will be testing it. So you can't really fully test it on Earth. And so some of the testing, some of the more important testing will be done in space. And so that will be one of the challenges. I know we have the DARPA Draco program, that one of the goals of that program is to test some of the nuclear thermal propulsion capabilities in space. That might be the hurdle that we'll be able to overcome. Any other questions? Well, thank you very much for having me. It was a pleasure to talk with you about these ideas and what we're working on. Oh, did you have a question?
Yeah, I did see pictures of like, I guess the mines. I think, well, anyways, there's a class here called Intro Space Exploration. We just learned about the NASA's Razor, like drilling machine. I don't know, I was just wondering what your thoughts were on that, or what Martin's plans were for extraction technology.
Yeah, there's some very interesting extraction technologies that are being developed by multiple companies and organizations, and we're looking at or keeping track of those technologies very closely because we're really interested in how to use them and how to enable this kind of economy to form. And we've developed some technologies ourselves at Lockheed Martin. And so I think the solution will be combining the technologies going forward in a way that can really help us get at that material, those resources.
So you said at the beginning, your group does a lot of that, searches out new technologies and figures out what needs to be developed. So can you explain more how that goes on?
Sure. So for exploring new technologies, we have a chief technologist in our group that tries to keep up on the latest technologies. Also, we do road mapping where we look into, that's where we look at what could be developing down the road that we need to keep an eye on as a potential way of kind of revolutionizing some of the way that we do things. So definitely just keep communications open, learning what others are doing, what other companies are doing, what other even international organizations are doing, so that we can keep on top of what's coming. Yeah.
So you mentioned that the Mars camp is being constructed with the gateway. Is that what you said?
Yeah.
So I guess would be the reasoning behind that. It's easier to propel it from the lunar surface up to the base camp. Are there other motivations though for doing it there as opposed to like lower orbit or anywhere else?
Oh, so what's the reasoning behind using the NRHO orbit for gateway?
Yeah.
Okay. So the NRHO orbits, NASA did a bunch of trades looking at various orbit options, and NRHO was ended up being a pretty good one because it has really good access to like the polar region, which is where a lot of our interest is because of the permanently shadowed regions in that area where you can find water. So it has really good access to the polar areas. It also you can access other locations around the moon from there as well. And then it can also serve as a hub for communication. So as a relay to communicate down to the surface and then back to Earth. So I think that kind of all of those helped or led to the selection of that site. I think they were also looking at, is it a good site for doing Mars missions? And it's a decent site for building up a Mars mission as well. Yeah.
What's the projected ratio between man and unmanned?
What's the projected ratio for the crewed versus uncrewed missions? I think we're going to see many robotic missions. And one of the exciting things about why we're going to see more and more robotic missions is NASA started a commercial lunar payload services program where companies have provided a commercially provided lunar lander that then you can get buy payload spots on these landers. And with that approach, it's really it's making the lunar surface more accessible, and we're already seeing that there are like a handful of missions that are already lined up to go to the lunar surface with this program. I think they're planning like a few every year, and they already have the next few years lined up for which missions are going. So we're going to see a lot of robotic missions going to the lunar surface with that program. So I guess if you think we're sending about 3 a year in this early phase, and then we're sending humans about once every other year, then I guess that's probably your ratio. And then some of those CLIPS missions will be sending rovers to explore the lunar surface. Some of them will be sending things to help to assist with the crewed missions, like the unpressurized rover that I showed in the earlier slides. So those CLIPS missions will be supporting the human spaceflight missions too. Yes.
Has there been any major red tape that you've run into with the government or Lockheed yourselves regarding the extension and like a nuclear?
I don't think so. I think that with nuclear technologies, that there's a lot of regulations around nuclear technologies, and so it's a matter of working with those regulations. So working with the government and making sure that you're following all the regulations that are associated with that. And then along with that, though, there's the ability to develop these kinds of technologies, but it takes a lot of coordination to make sure that you're following the regulations.
So do you see any motivation as far as pushing past Mars with crew missions? So for instance, there's other destination like Europa. Is there like any motivation for that, or is that just outside the scope of like economic feasibility?
So we've been mainly looking at crewed missions to the moon and Mars, but we are really interested in how could NTP enable robotic missions to Europa and other destinations and outer planets, because the NTP propulsion is so efficient and capable that it could really enable some really awesome robotic missions out there. Yeah. Oh, so how does NTP compare to ion propulsion? So the ion propulsion is higher efficiency, and then NTP propulsion is higher thrust. So the NTP propulsion can handle larger vehicles, like the Mars Base Camp.
More questions to what I just asked. Nuclear is something that the public sometimes has a hard time accepting because of the danger. Is that part of why you are only just now looking at nuclear, or was there another reason that didn't?
I think that, so why are we looking at nuclear now? So there's several things that are kind of coming together in this perfect timing. NASA is really interested in looking at nuclear thermal propulsion and nuclear electric propulsion. So that's another kind of nuclear propulsion. And so NASA is asking companies to do investigations into what kind of capabilities could happen from these kinds of propulsion. And it's to build up that Mars transit vehicle. We're finally at the point where it feels like building a Mars transit vehicle can actually happen, like in the next 10, 20 years, where we can actually start to see it come together. And then with the Draco program and testing the NTP technology, and actually getting that hurdle of testing in space, then that will help advance the technology to the point where we can use it. And then from a safety perspective, we have for Mars Base Camp this year, we had a safety engineer on our team that was looking at the safety of launching, the safety of the concept that we're developing. So there's things that you can do within the design to try and address safety concerns, both for the crew, and then also there are very good launch regulations around launching nuclear materials that really try to keep them safe for launch as well. Yeah.
So the government made this a priority. How quickly do you think we could put this all together and send out a mission to Mars?
So
This is
we've
like a
been-
priority like the moon in the 60s.
We've been looking at like early 2030s as when you could get that kind of Mars mission set up. And so NASA's been looking at like mid 2030s too. So mid to late 2030s. So I think that's where we're all kind of honing in on that could be a possibility.
Well, thank you again, Dr. Evers, for taking the enlighten us. And thank you for all of also for contact information if you'd like to reach out to us or Dr. Edwards. Are you okay with us sending out your contact info in our newsletter?
Sure.
Awesome. So you'll be able to get that. You can also join our engage page. Thank you very much.
You're welcome.